All right, so continuing our discussion about how we linearize data in the IB, here's an example that we went through in class. So you're asked to graph the gravitational force against the distance r between two masses, big M and little m, and I give you this equation. So you can see that when you graph this data, you end up with a 1 over r squared relationship. Okay, so it's an inverse relationship. Okay, so here's your sketch. All right, and in part B, I say on the same graph paper. So this is meant to be done by hand. Sketch a graph linearizing this data and determine what the slope of the line represents. Okay, so as we discussed in class, if you want to linearize this data, what you would do is make it of the form y equals mx plus b, okay, up top here, where your y value, your y variable is very obviously f, your x variable is 1 over r squared, and your slope is given by the quantity g times m, okay? So you have this situation here. Here's your 1 over r squared, which is your new horizontal or independent or x variable. Here's your force as it was before on the y-axis. And here's your linear fit right here. And the gradient is given by g times m. So what you could do is you could actually use this experimental value for the gradient, if these were experimental values, which they're not because you use an equation to find them. But if they were, you could use the gradient of your slope in LoggerPro to help you figure out the value of any one of these variables experimentally. So that's kind of what we are going to be doing for 2 years in this class. It's kind of the whole point experimentally of why we do what we do, okay? And the thing to note here is that f is proportional to 1 over r squared. F is not proportional to r, but f is proportional to 1 over r squared. Linear, and it goes through the origin. Okay. All right. Here's another example. We'll do a demonstration in class for this one, if you guys want to see this. Okay. The time period t of oscillation of a mass m suspended from a vertical spring is given by that equation. Okay. T and m are both experimental values. Turns out that t is the period, m is the mass, k is a constant. Okay. And I want you to determine what you would plot to produce a straight line graph and what the slope of the line would represent. So I'm not asking you to actually make this graph, but we could do it in class. In fact, we might do it in class using LoggerPro. Okay, all right. So pause the video and have a think about this. Okay, so here's my solution. All right, so here's my original equation. I would actually graph t against the square root of m, okay, where the slope of the line would be 2 pi over the square root of k, right? So here's my y variable, that's y, and square root of m would be my x variable, and then everything left over would then be my slope, okay? The other thing you could do is you could actually square both sides. This is also valid, a little bit easier algebraically, in which case you would then graph t squared on your y-axis and you would graph m on your x-axis, and then your slope would be 4 pi squared over k. Regardless of the method that you use, and we'll do this in class, regardless of the method you use, you'll end up with this, you should end up with the same value for k. All right? So pretty interesting. Note also that m is the independent variable, okay? And I'm actually making a star here. I'm saying number 2 is actually preferable. You could do either. 2 is preferable because you really want to avoid roots and any power that's not an integer, generally speaking. But again, you probably wouldn't be marked off for that. Okay? All right, next example. Okay, so you've read it. Go ahead and try this one. Okay, so again, what we can do, what we need to do, because we're the variables that we're dealing with are t and r. Okay, those are the things we're actually measuring in the laboratory. All right. Both of them are included in the right-hand side of this equation, so all you need is a little bit of algebra to separate them. Okay. So which one would be the independent variable? That's for you to figure out. So if you read the problem, a particle is moving in a circular path of radius r. The time taken for one complete revolution is t. Okay. The acceleration of the particle. Okay. So I'm saying you would actually graph y, t squared, against x, where x is r, okay? So in this case, r, yes, of course, in this case, r would be your independent variable, okay? And actually, you guys will do a circular motion lab like this, where you're varying the radius of something swinging around horizontally, and you're going to try to measure the revolution t, okay? So we have t squared against r, where the slope of the line would be that, okay? In this case, we don't have to deal with any square roots or anything. If we took the square root of t squared, we would get t, but then we'd end up with root r, which is not really necessary, okay? So r is the independent variable, okay? All right. Where x and y units are given in scientific notation, or anything but base units, you have to be very careful when you're interpreting the slope. Note the power of 10 and note the prefix, okay? Super important. For example, here's a graph of maximum kinetic energy against frequency for something moving, okay? Or must be a wave or something like that, not sure. Draw the best fit lines in these graphs and determine the slopes of the lines in proper units, okay? Well, the best fit line, there we go, it's that blue line. I think you would all agree with that, okay? When you figure out the slope, don't forget the 10 to the minus 19 here and the 10 to the 14. Okay, so the slope is clearly the rise over the run, which is delta Ke max over delta F. Okay, so here's my triangle right here. Okay, here's my delta F, and here's my delta Ke max. All right. Notice that it's not simply 1.3 divided by 2.1. If I did that, I would be off by many orders of magnitude. Okay, so you have to include the 10 to the minus 19 and 10 to the 14. Super important, and don't forget your units. Very, very, very important. Okay. Always remember also to use at least half your data when determining a slope. You will have points taken off if you don't do that. Okay, there's no reason to make a little tiny triangle right here. That wouldn't make any sense at all. Make a nice big triangle. Make it as big as you can and use all your data if possible. Okay. All right. Here's another one. So you want to draw the best fit line. And don't forget, this is 10 to the second and 10 to the 6 are the powers of 10 here. There's my best fit line. Okay, slope is rise over run. It's not 1.4 divided by 13. It's 1.4 times 10 to the second divided by 13 times 10 to the 6. Okay, so super important. Notice how I'm using lots of my data. I guess I could have used a little more, but as long as I'm using at least half of it, I'm cool. That's cool. I got 1.1 times 10 to the minus 5 Newton meters per Pascal. Okay. All right. Okay. Next one. This one's pretty interesting. Okay. This is a past paper question of, I believe, a force against distance of a spider web being stretched or something like that. A past paper question. Pretty cool. Okay. All right. So if you draw your best fit line, it's something like this. All right. That's what I would perceive that to be. Okay. This is kind of like the lab we did. The graph is not linear, so it doesn't make sense to discuss the slope, but you could actually discuss the slope for the linear part of the graph. Okay? All right? And you would get something like this. You would get delta out, you would get rise over run. It's your call. I got about 2.1 newtons per meter. Okay? Something like that, which is actually, that's a really strong spider web, isn't it? Wow, that's really strong. Okay? Okay, if it were quadratic, which it is not, then f of x would be of the form ax squared, okay? And then if you were to graph f of x against x squared, you would get a straight line with a slope of a. Again, this is not quadratic, but if it were, you could do that. So this graph is actually a piecewise defined function, probably. This part's linear. It looks like the linear part starts about at 3 and goes up here. This part is definitely not linear. You could figure out what that is. It might be quadratic. I don't know. But then you could analyze it as two separate problems, okay? If it were quadratic, then again, if you were to graph f of x against x squared, it would be straight and pass through the origin, which means it would be proportional, okay? All right, so in summary, the three most useful things we use graphs for in the IB. The number one, the most important thing is finding the gradient or the slope, okay? The slope is the rise over run. A linear graph has a constant slope, obviously. The slope always has units, and those units are crucial in IB physics in terms of figuring out what's going on physically with an experiment. Okay, don't forget the units. You always want to use the biggest triangle you can manage from your graph, at least 1/2 the data. The slope of a curve at a particular point is the slope of the tangent line at that point. So here's how you would draw a tangent line at point P if I were to ask you the slope at point P. So you can actually talk about slopes of curved lines, but only in an infinitesimally small x value, okay? And that's calculus, which you'll learn later, okay? Second, the y-intercept is also very important, okay? Remember, if it's a linear graph, it can only cross the y-axis once, okay? And in fact, if a function crosses the y-axis more than once, then it's not a function by the vertical line test, which we discussed in class, okay? In experimental data, this value, the y-intercept, has physical significance. It may indicate a systematic error. We're going to talk about that kind of error later on, okay? Only if a line goes through the origin, then are the two quantities proportional to one another, even if it's linear, okay? Very important. And finally, the area between the line and the x-axis will be important in this class later on. The area under the line often represents a physical quantity, and if the function is negative under the x-axis, we can actually have such things as negative areas in physics, and that actually means something physically important, which we'll discuss later. The area is the area of a trapezoid, and for linear data, that's easy. You can either use the equation of a trapezoid, or you could, like in this case, you could break this up into a square, or I'm sorry, a rectangle, and a triangle, and that would be super easy to find the area of those two things. The area has units. They're the y units times the x units, okay? When we do motion graphs, this will be your first experience doing this, where you're multiplying units on the y-axis and the x-axis. The area under a curve can be found by counting all the small squares under it and adding them all up if it's a curve, okay? If you know the function, you can integrate this, and that's what you do when you learn calculus, which you guys will learn later, okay? All right, I think this is our last example for today, for this video. Go ahead and pause the video and read this. Now, when I'm asking you on the graph to draw the uncertainty in the data points, what you could do is you could take a screenshot of this example, download it, and then maybe do it on your iPad or however you guys want to do this. It's very instructive for you to try these problems first on a separate sheet of paper or actually do it on the graph, okay? So give it a try. So the graph is some angle, or not an angle, sorry, it's temperature theta in degrees Celsius against distance x in centimeters, and it looks like these are temperatures along a copper rod. Kind of interesting, okay? So now we're dealing with uncertainties, and I'm asking you to draw the uncertainty in the data points, which is also known as an error bar for these particular points, okay? Here's what I got here, all right? Plus or minus 2 degrees Celsius. So if you look at the scale here, it looks to me like every box, 82, 84, 86, 88, 90, it looks like every vertical box is 2 degrees Celsius. So every error bar that you draw has to be one box above and one box below, okay, for a total length of 4 degrees Celsius, all right? And I've sort of exaggerated the ends of these, the horizontal part of these vertical error bars, just so that you can see them very clearly, okay? On the graph, draw the best fit line for the data. That's pretty easy. I expect you to be able to do that. Okay, use your graph to estimate the temperature of the rod at 55 centimeters. You're using interpolation for this. Okay, so that looks like that's about at 20 degrees Celsius. Okay, and again, you might get a slightly different value. You might get 20.1, 9.5, something like that. 21. I don't know what you would get, depending on your best fit line. We may all draw them slightly differently, but you would get something in the ballpark of 20. And on a test, you would have a range of values that I would accept a correct answer from. In this case, it might be, let's see, I don't know, 19. I probably would accept something from 19 to 21, maybe from 18 to 22 would be reasonable for this, given how you want to draw your line of best fit. And that's it.